Hello everyone, my name is Erica Cross and today I will be presenting on the distribution of the sample correlation in the presence of censoring. So I'd like to thank Dr. Linder for being my faculty mentor, and also I'm going to mention that the National Science Foundation funded my research. So we need to begin by taking a sample from a bivariate normal population. This means we have two values, an x and a y. So we would assume that there's an association between the x and y, and want to be able to make inferences about this association. In statistics, there's two measures of association. We have population correlation, which is represented by rho, and also population Kendall's tau, which is symbolized by tau. Even though I worked with both these measures, for the purpose of this presentation, we're going to focus on rho. So statistics is all about estimation of population parameters, such as rho, from samples. So, in order to gauge the precision and accuracy of our estimators, we need to look at the stochastic properties. In an ideal setting, we know the sampling distribution, and therefore estimation of the population parameters is straightforward. Unfortunately, not all data fall into this ideal setting. Many times we have restraints on our data such that the sampling distribution is mathematically intractable. One of these instances is censoring. Censoring implies that we have n bivariate normal vectors, but we only observe p of them with the smallest p values. So data that is subjected to censoring, we do not know the sampling distribution. So we're going to start by simulating 10,000 values of the absolute value of r. Looking at this histogram, we want to see what distribution could probably approximate the absolute values of r. So we're going to look at the beta distribution. So two questions arise. How do we fit the beta distribution, and how well does it fit the real sampling distribution of r? So why did we choose the beta distribution? Well, beta is a very versatile function, and it has the following density function. This is restricted between values of 0 and 1, which is very convenient because the absolute value of r is also bound between 0 and 1. The shape and skew of our beta distribution is determined by the parameters. We can see that an alpha of 6 and a beta of 6 create a very symmetric distribution. On the other hand, an alpha of 9 and a beta of 3 create a left-skewed distribution. So now we need to determine the parameters. We're going to start by simulating 10,000 absolute values of r under fixed experimental conditions. So with this large collection of absolute values of r, we're going to try to find our parameters. There are two methods for estimating our parameters. We have method of moments, and also we have maximum likelihood estimation. So we're going to start with method of moments. The beta distribution has the following properties for the expected value of x and for the variance of x. With our 10,000 absolute values of r, we're going to find the sample mean and match that to the expected value of x of our beta distribution. And we're going to match the sample variance to the variance of x of our beta distribution. From here, we can solve for our alpha and beta hat. And then we also looked at maximum likelihood estimators, and we used MATLAB to solve for our parameters numerically. Now, with our parameters, we're going to hypothesize that we have a beta distribution with parameters alpha and beta hat that will match our absolute value of r. But these parameters are no good if they do not provide a good fit. So we're going to test for goodness of fit. Now, we're going to pretend that our beta distribution looks like the following. And then we're going to divide this into equiprobable bits. So we have 10 of those. We're going to generate a new sample of 2,000 absolute value of r and put them in their respective bins. With this, we're going to compute the test statistic, which is the sum of the observed minus the expected squared over the expected. And then we'll look at the probability that our test statistic is greater than or equal to this chi-square value with degrees of freedom equal to bins minus 1. And this will be our p-value. So now we're looking at the test statistics and p-value for estimated parameters when n is 20 and rho is 0.5. We would hope that our test statistic was 9, but unfortunately, both the method of moments and the MLE do not have very promising results. They both have very poor overall goodness of fit. But luckily for us, we have another means to test for goodness of fit. So we can use percentile estimation instead. The T column represents the simulated percentiles using the R program. And then we use the beta distributions for both maximum likelihood estimators and method of moments to get percentiles. When you look at the error, we can see that the left tail has poor fit. On the other hand, when we move to the right tail, it has a decent fit. And so this is a pretty good result. Even though this is very preliminary, I would say, just from looking at this table, that it appears that the method of moments technique may have better fit for the tails. So when n is large, the asymptotic distribution of R is known. Fisher proved that when n is small, the z is approximately normal with mean 0 and variance 1. We have the following confidence interval for the natural log of 1 plus rho over 1 minus rho. So from here, we can manipulate the function to have the confidence interval for rho. So we have the question, how does the actual confidence level compare to the nominal confidence level when the data have been censored? We can see that as rho increases, we have less data fall into our confidence interval. Also, we can look at the power of the test, which is the likelihood of rejecting a false hypothesis. So obviously, the stronger the power, the better. We looked at both simulated power and theoretical power, and we noticed that as rho increases, power increases, and as there's less censoring, power increases. But another question arises as what combinations of N and P will result in a desired power. So looking at this, we can see that as rho increases, you're allowed to censor more and you will still meet a specified power. Also, if you look at this box right here, we can see that as a percentage, for n equals 20, you need 90% of the sample in order to have 4.4 power. On the other hand, when n is 60, you only need 50% of the sample in order to meet that same power. So, further research in this field, we could look for a regression, use regression to find a function to find our alpha and beta. So if a researcher has an n and a p, we can give them their alpha and beta so that they know what beta distribution they're looking at. We can also look at the power of the test of the null hypothesis of rho equals 1 against the alternative hypothesis of rho not equal to 1 using the beta distribution. We could evaluate the confidence intervals for rho formed by inverting the beta distribution. And finally, instead of using the absolute value of R, we could directly approximate the distribution of R instead. So, are there any questions?
Eventually will be applied to real data coming in from some people, and it looks like you were using the absolute value of R to kind of simulate what that data might look like. At what point do you think it would be ready to start looking at outside data sets? And
if we can find a way to make a function to get the alpha and beta from an n and a p, then it could be used by researchers. They would just be able to use the function to find their own alpha and beta, and then they'd have their beta distribution on that. So
we have set functions. We're working on this.
we're working on them. They're not working so well, but we're getting there.